All right, everybody. So I was thinking about doing voices for these things, but at the same time, I'm not really good with extended voices, and I'm not feeling so great. But let's kind of work on some of these Khan Academy assignments, see what we can do. All right. So one of the first things I want to do is I'm going to go through each one of these. It's going to be kind of a long video to kind of remind you of different things. But let's talk about this one. A lot of students have been struggling with this one a little bit. And I just kind of want to make sure that we go over it. So it's a lot easier than you think. Basically, this is just substitution. So we have something that says P is equal to negative 4b squared plus 6b minus 9. And we have another thing that says that Q is equal to 7b squared minus 2b minus 5. What's nice about this is that there's nothing magical or fancy about what we're going to do. We're just going to plug it in. We're just going to substitute. So just a quick reminder, whenever you have an equation that says something equals something else, that means that they're the same thing. It means that they're interchangeable. So anywhere you see a P, you can replace it with all of this stuff. It doesn't just stop here. You could totally do it if you had like some random thing. Let's just do a little thought bubble. 5 plus x is equal to 7 plus y squared. If you ever saw an equation that said 5 plus x plus, I don't know, like 10 plus 2x equals, I don't know, y squared, then you could totally just say, all right, well, let's combine these like terms. You get 15 plus 3x equals y squared. And then you could factor out a 3. Remember, that's just reverse distribution. And then you can replace that 5 plus x with what it's equal to. Now, you would never really do this. It's just I'm showing you your options and your freedom. You could totally replace it with what it's equal to, 7 plus y squared. And then just kind of continue along like you would normally do and then solve this equation. Now, we're not going to have to do anything like that, but that whole idea was literally just saying if something's equal to something else, you can replace it. They're interchangeable. They are the same thing. So for our actual problem right here, we have P is equal to that stuff, Q is equal to that stuff, and I want to find P minus Q. So I'm going to write P in red, P minus, and I'm going to write Q in blue, just so you know where everything's coming from. So instead of writing P, I can write what P is equal to. And instead of writing Q, I can write what Q is equal to. And then all I have to do is simplify. So notice this has a negative in front of these parentheses. If we want to get rid of parentheses and there's something in front of it, then we need to distribute it. So in this case, it's an invisible -1 on there whenever there's just a negative, just like when you have 7 minus 4. You can think of it as 7 plus -4. Same thing here. You have this stuff minus this stuff, so it's the same thing as this stuff plus the negative of that. There's an invisible -1, and we need to distribute that. That's why I wrote my parentheses, to make sure I didn't mess that up. And I'm left with, on the left side, there's an invisible 1 outside of here that you can distribute. But most of the time, we don't even think of it like that. We just take those parentheses away if there's nothing in front of it. But it's like a little +1 that it distributes. It just doesn't do anything on that first set of parentheses. And on that second set of parentheses, I distribute the -1 onto everything. And I get -1 times 7b squared is -7b squared. -1 times -2b is +2b, and then +5 when I distribute that -1. It just changes the signs when it's just a -1. The negative is what's changing the sign, really, and then the 1 itself is not doing anything because it's identity. Now I need to combine like terms. Now this is a thing that students goof a lot. Students try to combine things like these two, but we can't do that. We've got to remember that they have to have the same number and types of factor. If you need a reminder, when I say number and types of factors, I mean b squared is equal to b times b. I have two b's being multiplied, and they are both b's, so whatever they combine with has to be the same. You have to be able to say it in English. If I can combine these two because it makes sense to say the words, I have negative 4b squareds minus 7b squareds is negative 11b squareds. It's easy to say it in English, but if you try to combine these two, you get negative 4b squared plus 6b, and then suddenly you've had to change something. You have to kind of guess, is it going to be b squared or b at the end? Is it going to be something else? Should not have to think about that. It should be just said in English, negative 4b squareds minus 7b squareds is negative 11b squareds. Just like 6b plus 2 more b's is plus 8b's, and negative 9 plus 5 is negative 4. And that would be your answer. Negative 11b squared plus 8b minus 4. Now this one gets students a lot because of the words. The words. They do it in the wrong order and they get it wrong. We're trying to subtract this from this. Now, just remember what your words mean in this case. If you're subtracting this thing from this thing, let's underline these in the correct color just to kind of separate them. If you're subtracting that red expression from the second one, then that red expression will be what is subtracted. So you're going to write the thing that you're subtracting it from first, and then you will subtract what you're subtracting from it, just like normal. And you can throw up some parentheses if you want. They're not super necessary on this first one because there's going to be an invisible 1 in front of it. But on the second one, to remember to distribute, we kind of need that. I get my 8y squared minus 5y plus 7. And I'm going to go ahead and I'm going to distribute this negative onto every single thing right there. And there's a little invisible 1 right here that you would distribute, but it just doesn't do anything. So you can drop the parentheses if there's nothing out front. No signs, anything like that. So this doesn't change, that first one. But this second one, when I distribute that negative onto all of those, it's going to swap the signs of what was originally there. And then I'm going to combine like terms. I have 2y squareds minus 8y squareds is negative 6y squareds. I always like to start with my highest power term and kind of go down. And then I get 7y plus 5y is positive 12y. And then 11 minus 7 is positive 4. So I'm sitting with a negative 6y squared plus 12y minus 4. Is that what it said? Plus 4. And I might have made arithmetic mistakes, but either way, I didn't. Yay! All right, so on this one, we're going to kind of go ahead and work with equations with parentheses. So again, these aren't super bad. It's just solve an equation. So we need to isolate our variable, whatever that is. So I've got this stuff equals this stuff. So I need a statement that says G is equal to some stuff. So I'm going to use my algebraic operations in reverse of order of operations. So that's how I like to do it. You don't have to do it that way. And order of operations is just a memorization strategy anyway to understand the rules. But either way, first thing I notice, I have some parentheses with some stuff outside of it. So I need to distribute. So let me go ahead and do that. 6 times negative 2g is negative 12g Remember, it's multiplication when you do that. You can actually write this out as 6 groups of that stuff, 6 groups of this stuff, add them together, combine like terms, and you'll get the exact same thing. You can confirm it for yourself. But then 6 times -1 is -6. Keep my equal sign. Everything else stays the same. I'm just distributing. -1 times 13g is -13g, and -1 times 2 is -2. And now I just really have to finish solving, just kind of simplify. So I don't care where my g's go. They can be on the left side or the right side. It doesn't matter. Sometimes it's easier for signs. I notice that the larger coefficient is on the right side. And so me personally, I think adding 13g is to both sides is easier. And again, my goal is to cancel it on one of the sides so it's not there. I want to get it in one spot. So I'm going to add 13g to both sides. And again, I'm doing that to make this happen because it's problem solving. I could have added anything I wanted to both sides and followed through, but adding this is the most convenient. If I do something else, I'm going to get more complex, more annoying stuff happening. So on the left side, I have -12g plus 13g is +1g. The -6 is unaffected. And on the right side, I get -13g plus 13g is 0. That's why I wanted it to go away, because when you add 0, it doesn't do anything. It's the additive identity. So this and this cancel with each other or add together to be 0. And I just get -2. All right, well, now I still have a -6 on the side with my g's, so I'm going to go ahead and add 6 to both sides. I like doing it on the same line to not have y'all think that there's something magical happening below. There's not. But again, I add 6 to both sides because I want this to happen. I want it to become 0. So I have g, -6 plus 6 is 0, so I can write the plus 0, but I'm going to not want to over time. And I get -2 plus 6 is the same thing as 6 minus 2, which is 4. So my final answer is 4. Same idea here, but what students do on this one is, for some reason, they forget their order of operations. They forget how distribution works. The only thing here that is being multiplied onto these parentheses is this -2. And if you want to write the plus -2 times that stuff, you can. It doesn't really matter. It's all the same. But either way, the negative gets distributed on both of those. That 3 is unaffected. It is separated by plus or minus. So it's a completely different operation in between the 3 and that other group of stuff. So when I distribute that -2 onto the 9, I get -18. And the -2 onto the 2m is -4m. On the right side, I just have m. So notice that 3 did not jump into the fray and start attacking or multiplying against the other stuff. It just stayed there. So maybe simplify a little bit. Again, optional. You can do it a different way to where you do it more, where it takes more steps. But I like efficiency. Simplifying that 3 minus 18 to -15 ends up being kind of a better strategy. Now, me, with my biased way of doing things, I like to think to myself, I kind of want to add that 4m to both sides. And the reason I want to do that is because it'll make it to where I don't have to make sign mistakes. So I get to add or subtract whatever I want from both sides of the equation without changing the solution set. But I want to add 4m, because if I add 4m, I get a positive on my right side and I'm less likely to make mistakes. Now, you don't have to do that. You could have totally subtracted 4m from subtracted m from both sides, then added the 15 to both sides, and then done it. But if you had done it correctly, it'll be the same. But the doing it correctly part kind of throws students off sometimes. So I like to get my positives, a positive on my variable instead of messing around, because I could easily make a mistake. So the -15 doesn't combine with anything on the left side. And then the -4m plus 4m is 0 when they combine. On the right side, I have m plus 4m is 5m. Students often forget that this invisible 1 out front of the m is there if it's not written. You have an m, and you're adding 4m. You have 5m at the end of it. All right, now let's undo the operation that is currently there on my m. I want m by itself. So I have a 5 being multiplied on it because it's sitting right there. So I need to undo that. So I'm going to either divide both sides by 5 or multiply both sides by 1/5. They are the exact same thing. But the 5 over 5 becomes 1, which is identity. That's why they cancel, because 1 times m is just m. And then negative 15 over 5 is negative 3. Now, some students are fine with saying m is equal to negative 3, so that's your answer. Some students have to have it on the same exact sides. So you can use the symmetric property of equality to kind of flip these two sides, as long as nothing changes about the individual sides. So your final answer should be negative 3, unless I made an arithmetic mistake, which I did not. All right, well, let's talk about parts of algebraic expressions a little bit. Okay, so we want to use the expression blah, blah, to find an example of each kind of expression. Okay, so we need to find a quotient, a sum, and a variable. So I feel like we just move them. All right, so my strategy for something like this is just to kind of deal with it one part at a time. So let's look at quotient. Quotient means two things that are being divided. So I'm looking for something with a division symbol or a fraction, because the fraction bars, if I remember correctly, I feel like it's called a vinculum. The fraction bar right here means division. In fact, the division symbol that you're used to means a fraction. If you look at it, it's the numerator and the denominator. So like if it's like 5 over 2, this dot right there represents a numerator, and this dot right there represents a denominator. So this can be rewritten as 5 over 2. Just a little handy-dandy reminder just in case you had forgotten it. But either way, we're looking for something that is a fraction or has division. The only thing I see is that one. The next one we're looking for is sum. So sum just means that there's an addition sign present. So this one is the only one with an addition sign present, so it's the only one that I can think that it could be a sum. And then this one's the only one that's a variable, so that's got to be that one. Complete the statement to describe the expression. This stuff. The expression consists of so-and-so factors, and each factor contains so-and-so terms. Well, just remember what a factor is. If I had 5 times 2, then this is one factor that has one term, and this is one factor that has one term. But if I rewrote each one of those, like we wouldn't want to do this. That's 5 ones being added together, which is the number 5. And this is 2 ones being added together, which is the number 2. So I could say that this is one factor with 5 terms, and this is one factor with 2 terms. Nobody would do that. But if you're ever just wanting to have a little bit of fun, go ahead. So I look at these things and I say, okay, I have one factor right here. Even if it looks weird, it's a group of stuff multiplying against another group of stuff. It's one single factor. It cannot be simplified. And then this one is another factor. Each one of these, so we have 2 total factors, and each of these factors contains 3 terms when you just count them up. So you have 2 total factors and 3 terms in each. So at the end of the day on that last one, you'd end up getting 6 total terms when you do the distribution, or 9 total terms when you do the distribution. Which expression represents the sum of exactly 2 terms? So we're looking for a sum. So let me just highlight the sums. We have this one is a sum, this one is a sum, and this one is a sum. This one is not a sum. It is x times y, which is called a product. Now that I've isolated those ones and gotten rid of one that's not so great, I need to look at the ones that have 2 terms and not 3. going to get rid of this one because it has 3 terms. So it looks like I'm just looking at B and D, and it lets you choose 2 answers, B and D. What is the coefficient of the term 12p in the expression 12p plus 9q? Well, the coefficient is always the number that's being multiplied on the variable. So that's it. It's just 12. Once I can type it. Consider the following expression and determine which statements are true. All right, let's look at each one of them. So we need to figure out which ones are true. The entire expression is a sum. So I have some stuff being added to some stuff, being added to some stuff, being added to some stuff. So I feel like this one is true unless they're not liking the idea of those quotients there. The coefficient of S is 3. Well, if you look at S, it's not 3. We need to remember something. S over 3 is the same thing as 1/3 times S. Because you can write S as S over 1 and do top times top over bottom times bottom. But again, we usually switch between these depending on what's more convenient. So these two things are the exact same thing. So let me just show you. If I take 1 over 3 and I multiply it times S, that's the same thing as multiplying it times S over 1. Because anything over 1 is itself. And then I can do top times top, 1 times S to get S, and bottom times bottom, 3 times 1 to get 3. So that right there shows that those are the same thing. So in this case, when it says the coefficient is 3, it's not. That is a false statement. The coefficient on S would be 1/3, so it's not going to be that one. The term 7 over R is a quotient. I'll agree with this, because a quotient just means division, which you can write with a division symbol or a fraction bar. So this is also true. And the term 2 to the 3rd power has a variable. It doesn't look like it does to me. Nothing varies there. It is always 2 to the 3rd power. Both of those are numbers, no letters, no abstract ideas. So it's literally just the number 8 at the end of the day. So we don't have to guess or solve for anything or anything like that. So it looks like those are the only 2. Evaluating expressions with multiple variables. All this one comes down to is another bit of substitution. So I have C over 2 minus 3 over 6 over D. Doesn't matter really what it is. All I've got to do is anywhere I see a C, I replace it with a 14. Anywhere I see a D, I replace it with 3. So C over 2? Nah, I don't see that anymore. I see 14 over 2 because my C is 14. And then the whole thing minus 3 plus 6 over D, but I don't see the letter D anymore. I see the number 3. Let me color code this a little bit better and actually remember what I'm using for my specific colors. It doesn't like it when I change my colors. So C was 14, D was 3. I just replaced them. And at the end of the day, I got 7. 14 over 2 is 7, minus 3, plus 6 over 3 is 2. So I got 7 minus 3 is 4. And 4 plus 2 is 6. Unless I made a tiny goof. Evaluate this stuff at these values. Again, we're just substituting. So P is equal to 8 and Q is equal to 6. So instead of writing P, I no longer see that. I see an 8 now. And then we have plus P times Q, but I don't see a P anymore. I see an 8. And I don't see a Q anymore. I see a 6. Remember, when they're sitting on top of each other like this, it's a long, fancy word called multiplication by juxtaposition. Multiplication by their position sitting on top of each other like they are means it's implied that they are being multiplied. So 8 over 4 is 2. 8 times 6 is 48. So my final answer should be 50. Unless I made a tiny arithmetic mistake, which happens. Simplifying square roots will be another video. It is a whole thing. It's not that they're that hard. It's just that they are connected so intrinsically to exponent properties. I want to make sure to get the background for everybody. But anyway, you have a good one.